Okay, so welcome everyone to this second week of ADS-CFT 20. So we have a new set of speakers and new set of attendees, and I'm very glad to see many of you. So on behalf of all the organizers, welcome, and I hope you enjoy this week to everyone who's come from outside. So our first speaker today morning is Gilad Lifschytz, who will tell us about a new perspective on bulk reconstruction.
Thank you very much. Good morning. Thank you for the organizer for having this opportunity to present this work. What I will talk today is based on two new papers in the last year with Dan Kabat, and we shed some new light on the program of bulk reconstruction, which I will also describe briefly for you. So, okay, everything is about ADS-CFT this week, so I guess I don't need to say much about it. I guess for many, one of the major points of ADS-CFT is the possibility that it will tell us something about quantum gravity. But for that, we really have to understand the ADS-CFT somewhat better. Clearly, the bulk ADS is some kind of organizing principle for the CFT, and you want to understand how this organized principle is exactly works, and maybe why. So one way to explore this is to ask, how do the degrees of freedom of the CFT combine together to make something of the bulk? And more specifically, we'll try to do that for the low energy physics of the bulk. That is, one tries to see how the CFT degrees of freedom organizes into bulk fields propagating on a fixed background. And hopefully, when we understand this, we'll understand why it is a natural thing for the ADS or any other space-time to arise from the CFT. So, a little bit of formulas. What we want to have is some operator. So all the operators that I will be talking about are always CFT operators. All expectation values that I'm writing are CFT expectation values. So what I said was that we want to find CFT operators, which I write as phi of Z1 and X1. Z is the coordinate which is perpendicular to the boundary in this case, and X are the coordinates of the boundary of the CFT. And we want to have some operators where we compute the CFT correlation function. It will give us the bulk results of fields propagating on the background, like we would do just perturbative field theory on background. So one way to start to do this is to, in fact, do perturbation theory in 1 over n. So when we have correlation functions, two-point function would be normalized such that they will be order 1, 3-point function 1 over n, 4-point function 1 over n squared, etc. And then it was in the early days of ADS-CFT, you can just do free fields and then deduce what would be the correct bulk operator for this to work on a level of a 2-point function. And one can write it in various ways, but it turned out to be very useful to write it in a way of a smearing function. So this is an expression where this phi 0 is a CFT operator. O is a conformal primary. In this case, I'm giving example for scalars. So it's a scalar conformal primary in the CFT. And K is called a smearing function. And one can deduce what K is by solving some kind of bulk equation of motion, in this case, the free bulk equation of motion. And we also have the condition that we want that the operator, as it goes to the boundary, scales like z to the delta, where delta is the conformal dimension of the scalar times the operator itself. So an example is that if you write things in this way, some integral of the boundary operator, then the claim is, and it's, well, you can do the computation, that the 2-point function of this guy in the CFT would give you the 2-point function of the bulk of a scalar field, of a free scalar field propagating on the ADS background with a mass square which is related to delta in the usual way. But of course we want to do not only 2-point function, we want to do 3-point function, etc. And one way to do this is to start with the bulk equation of motion. So let's say you have some scalar field with some equation of motion of this form. You can expand it in this way, and then plug this into this equation. So if you plug this into this equation, phi 0 solved just the free equation, then the solution was given before, and then if you plug it, phi 1 would solve an equation like box squared minus m squared phi 1 is 1 over n phi 0 squared, and that could be solved by using what is called space-like Green's function. And in this way, phi 0, phi 1, and later phi 2, etc., can be written as some integral of fields in the CFT, or in this case, living at the boundary. So this is a proof of concept. If we had the bulk theory, we could indeed write CFT operators whose expectation value will be the right ones. But of course, we want to do better and not necessarily know the bulk theory, but deduce the bulk theory, or at least see somehow from the CFT how this arises. So let's say you have phi 0 and you don't want to use the equation of motion. Can you do somewhat better? Well, it turns out that if one puts phi 0, the guy that solves the free field equation of motion, inside a 3-point function. So this dxi ki of phi I is really my phi 0, and it's with a 2-point function with two other boundary operators, oj of y1 and of k of y2. Now, of course, this is not going to be the right answer, because this will not solve the correct equation of motion. And now it could be just wrong, but it turns out it's wrong in an interesting way. So this integral is given by this expression. The important thing here is that this is a hypergeometric function, and so it has some branch cuts, and that this chi is some combination of the bulk and boundary coordinates, which I will talk in a minute about. So the way that we do this, of course, we want to avoid any kind of singularities. And you might worry that, is this well defined? Because this could have singularity in the region where I smear. So the way you usually do it is you take these operators far enough from each other that this integral is well defined. You get some answer. And then when you want to go to a range of parameters where in principle could have been problematic, you just analytically continue. Okay? This is the usual way we do in field theory. So, however, this function has two singularities on a branch cut. There's a singularity at chi equal to 0, which is fine. Chi equal to 0 singularity is exactly when the bulk operator is light-like from one of the boundary operators. So that's something we're used to. However, there's a singularity at chi equal to 1 and a branch cut between chi equal to 1 and 0. And this is problematic, as I will explain, but first, why does this arise? So, in order to see a good way why it arises, I'm going to use the fact that these people have understood. This is actually an interesting point that in some ways this OP block expansion was already known in 72, and the way that we wrote this was actually using a Bessel function that they could have deduced ADS field propagating, but it was not done at the time. So anyway, O1 of Y1, O of Y2, you do an OP expansion. The OP expansion is in terms of families. Let's say we only have scalars here. So conformal families labeled by K. And each, in the sum for each conformal family, there's a sum over the descendants with particular combination. And it turned out that for any conformal family, the particular combination is such that it can be written as an integral over a bulk geodesic which connects y1 to y2 of the field phi 0 that I just wrote before. And so you can understand the chi equal to 1 singularity is actually when another, so this is Oy of y1 and y2, and if I look at this guy here, so this I can replace with this integral of phi 0, and then when the other phi 0, which is somewhere in the bulk, approaches this geodesic, there would be a singularity. In fact, when it approaches this geodesic or the light cone emanating from it. So this chi equal to 1 singularity is, you can understand in this way. The problem is that this chi equal to 1 singularity is not very good. So if you look at this and this chi equal to 1 singularity, this 3-point function will not obey bulk causality. This singularity happens when all 3 points are bulk spacelight separated to each other, and so the correlation function, the correct correlation function, should be analytic there, and it's not. Okay, so what to do? Well, clear, yes?
When you turn on 1 over n interactions, you expect there's some non-locality just because of the Gauss law. So presumably some of this is gauge dependent, and I agree, of course, that you should, you need to modify the expression for phi 0, but I just want to make sure that how do we exclude, the fact that we do expect some non-locality because of the Gauss law?
I will talk about this, but notice that this is really just some scalar field theory. This has no gravity, or necessarily the scalars are not charged under anything. So this problem is not due to some Gauss law, although the fact that you do have some non-locality is correct. But you don't expect non-locality in this case, but I will talk about this also. Okay. So, how do you correct this? Well, clearly you have to cancel this chi equal to 1 singularity. And so the way that it was suggested to do is that you start with your phi 0 and you add a particular combination of the phi j and phi k's, which here I called phi n, which are some tower of double trace operators built from the phi j and phi k. And now if you insert this guy here in this correlation function, you ask that the result will not have this chi equal to 1 singularity. And this fixes the ANs. And in fact, this can be done in many examples explicitly, and you find the ANs that do this. And in fact, after you find the ANs, which again, you just do for reason of canceling chi equal to 1 singularity, that is having the correct bulk analytic condition, then it turns out you can compute, for instance, the equation of motion that this guy solves, and it actually turns out to be the correct equation of motion. ANs are not unique, but their non-uniqueness is exactly the freedom of bulk redefinition that preserves the one-over expansion. And if this was indeed charged under some gauge field, or if we were talking with 3-point function with energy momentum tensor, the resulting expression would give the correct transformation law under ADS isometries. So this can be done. You can extend this to 4-point function and 5-point function and 6-point function, and certainly at tree level, although the loops have not been worked out. But in fact, it is not a very satisfactory construction. And why? Well, first, you needed the bulk metric in order to compute phi 0. Yeah. Yes.
What data enters this AN CFT at the lowest order? Is it just completely kinematical, or does it depend on various 3-point couplings?
It would depend on the 2-point, well, it depends on the 2-point coupling.
Okay, so it depends on delta, but that's it?
Yeah.
Lots of locality you got was proportional.
I could not hear you.
the previous loss of locality you got was proportional to the 3-point function.
Yes.
So this ANs, to cancel that, must also depend on the 3-point CID. There must be a 3-point function coefficient that...
Yes, it's proportional to that.
So a 3-point function.
But also, if you normalize the 2-point function a certain way, so it depends on how you normalize, for instance, the 2-point function of the double trace operators, of course, that would mean.
But also on the 3-point...
But also depends on the 3-point function. It's a linear in the...
Okay, I understand. Okay, so
if you do it, for instance, to higher order, to the 1 over n squared, to the 4-point function, actually, this construction,
so roughly speaking, it involves all the double traces that phi I can couple to.
Yeah, these are the double traces. It's not what the phi I couple to. You need to add here something that would have non-zero 3-point function with the phi j and the phi k.
Yep.
So that's why it's made out of double trace operators of the phi j and phi k.
Yeah. But you have to do that for all the possible OJ and OK of the theory.
That's right. Yes. So there's a tau for each non-trivial 3-point function that you have to add. Okay. So why is this not satisfactory? Again, the phi 0, originally, we had to know the bulk metric in order to deduce it. We had to solve some free field equation motion. Maybe we don't need the interactions, but we certainly need still to know the background and to know the bulk metric to deduce the smearing function. Another point is that while you could phrase it in such a way that you want the CFT correlation function to be analytic and chi equal to 1, it really comes from a bulk argument. If we just looked at it, why would we in the CFT ask for this condition? And as Raju said, actually, bulk correlation functions don't obey locality. For instance, when you have interaction with the gravity or with some gauge field, there's Gauss constraint, and there is particular things on the boundary which do not commute with the bulk field. And while you could avoid this, in a technical way in this case, by looking at particular type of correlation function, in fact, it doesn't seem to be such a good principle to invoke as a basic principle in order to do bulk reconstruction. You could ask more philosophical kind of thing is that, well, okay, we had phi 0 from the bulk equation motion, clearly it's not correct, but it was not correct in an interesting way, and it's not so clear why. As I said before, it could have just been wrong, but still without any clues to what is right in this way. And the last point is, what about entanglement? Okay, some people think space-time entanglement are related to each other. We see no evidence of any kind of need for entanglement ideas in this construction, and it would be nice to have something to do about it. So what I'm going to talk about is some new perspective on these issues that has been understood in the last year. Okay, so let's talk about the modular Hamiltonian. So we have a CFT and we have some region. Well, I guess that's before that. So the modular Hamiltonian, given a density matrix, the modular Hamiltonian is defined this way. It's an operator. The density matrix is an operator. And the modular Hamiltonian generate what is called modular flow, which is something basic in constructive field theory. I'll talk about density matrices that are given by taking some traces over space, time in space in this case, in the CFT. So let's say we have some region A in the CFT, and we can define a density matrix by tracing all the complement region. So we get H mod A. And we can also do that, the same thing for the complement region, which is called A bar. So we trace over A, and we got H mod A bar. And we can define what is called a total Hamiltonian, which is H mod A minus H mod A bar. And this has a very nice thing. This is a well-defined operator. It doesn't have singularities in the way that the other two have, and it annihilates the state, the pure state that we started with, that we got these matrices from. For spherical region in the CFT, in the ground state, we know the expression of the modular Hamiltonian. This was work done a few years ago. Yeah. I cannot hear.
So why is there a relative minus sign and not a plus sign? Is there a some
Yeah, this is how it is. I mean, maybe a more intuitive thing is that if you know about the black hole, you look at like extended classical diagram. There is a Hamiltonian on the left and a Hamiltonian on the right. But the one that is smooth is that the time goes downwards on the left and upwards on the right. That's similar to this situation.
Another way would be that you want e to the h mod to leave the state invariant. And it'll do that if this. So in the black hole case, it happens because HL minus HR is an isometry, but in general, this operator, e to this, yeah, just by demanding it should leave it invariant. The modular operator, which is e to this guy, should leave the state invariant. So.
Yes, this is the one that is nice. It also has no singularities and fine. Okay. Now, if we have a gravity dual and a region A, we can do what we have here is the example. So here is the boundary. It's here in this case, it's a line. So it's like ADS3, CFT. We have the region A, which is in the red. There is what is called a Rutakanagi surface, an RT surface here, which in this case is just a geodesic that connects the two endpoints. And that defines, for the region A, some region in the bulk, which is shaded here in blue. And this RT surface always separates the bulk into two. One is the region which is connected to the boundary, and one which to this region of the boundary, and one which is to the complement. And so you can do, you can have a bulk modular Hamiltonian for this region and for its bulk complement. Okay? And you can define the bulk total modular Hamiltonian in the same way as having the difference between the two regions. And it turns out that the action of the bulk and boundary modular Hamiltonian are identified. This is the work by GLMS and around years ago. So they act the same way on objects that we have. In particular, if I have an object, phi, in the bulk, I can think about it as a bulk field, and if it's a scalar object, and if it's on the RT surface, since the RT surface, here it's a little bit hard to see, but really this surface is a bifurcation sphere for the action of the modular Hamiltonian, which means that scalar objects sitting on the RT surface commutes with the modular Hamiltonian. The modular Hamiltonian usually induces a time or modular time evolution. On the RT surface, that time evolution is a fixed point, so scalar objects would commute if they sit on the RT surface with the modular Hamiltonian. So what does this mean? It means that if I take some operator in the CFT that's supposed to mimic the bulk field, and it would commute with any CFT modular Hamiltonian whose RT surface goes through the point for which this operator is supposed to represent something in the bulk. So for instance, here is an example of ADS3, and I have two modular Hamiltonians. One modular Hamiltonian which is based on two endpoints, 1 and 2, and the other modular Hamiltonian based on 3 and 4. They intersect at a point, okay? So clearly, if I find an object in the CFT which both commutes with H12 and which H34, it must be localized at this point, okay? And it also must, of course, commute with any modular Hamiltonian that has its RT surface going through that point. Okay? So there's an infinite set of modular Hamiltonians that would commute with that set. But of course, to fix it, it's enough to solve 2, and you can then check at any others. Okay? So this can actually, as I said before, this is in ADS3, so you just need two surfaces. In higher dimension, you need more in order to intersect for a point. So in the ADS3 case, you can write the modular Hamiltonian in this way, where Q0 is the generator of the conformal transformation, the special conformal transformation in the time direction, P0 translation in the time direction, and M01 the boost in the 0-1 direction. And so you know exactly what this modular Hamiltonian is, and you can just solve these two equations to see what you get in the CFT. Okay, this is a CFT computation. And as you might suspect, the solution is exactly the phi 0 that I wrote before. So in fact, for any operator, primary scalar operator in the CFT, with a conformal dimension delta, this would be a solution to these equations. And of course, these equations are linear, so any linear combination of them would be a solution. Now, this is clearly something that can be generalized. That is, any state that you have in the CFT, you could write, in principle, the modular Hamiltonian, and you can use these conditions. And in fact, at least for ADS, for CFT2, there is another known simple modular Hamiltonian, which is the one for finite temperature, and you can do the same game, and you can compute the smearing function, or what I called here phi 0 for that, and you find the correct expression for the BTZ black hole, at least for the outside region. Okay, so this seems to be a prescription for getting the smearing functions in any state without knowing the equations of motion. Now I should say that I've a little bit cheated here. So if you look at these equations, it's a little bit. If I have a solution phi, if I multiply by any constant, it's also a solution. And that constant could be a function of the space-time coordinates. Since this is a CFT expression, it doesn't know anything about the space-time coordinates, which are just variables which are related to the endpoints of the modular Hamiltonians. So any function times phi of space-time coordinates would also be a solution. This is fine. These equations should be thought of the equation for having something which is local. If you have a bulk field, you multiply by some function, local function, it's still a local bulk field. You just have different correlation functions. However, during this procedure, you actually get more information. For instance, as you can see, this intersect at some point, and you can now start moving the 1 and 2, and basically you get the equation for the geodesics. So you can get the equation for the geodesics from this procedure. This is just part of the solution. And so using that and some other tricks, you can actually, in simple cases, fix this expression to have the canonical bulk singularity that you know. And that fixes that coefficient. But actually, it's not so important for the rest of the talk. Okay, but this is nice, but it raises a new question. Okay? So the procedure that I outlined here makes it very clear that the thing that I get is something which has to be localized at the intersection point. Now, before, when we thought about phi 0, we thought, okay, it solved the free field equation of motion. And so it's clearly not correct as a local bulk field. For instance, 3-point function, 4-point function could not work. But here, from this point of view, it's completely unclear why phi 0 is not a good local operator. So what is going on? I mean, we before had 1/n corrections, but the modular Hamiltonian is exactly known in the vacuum. There's no 1/n correction that we need to add. So we know exactly the equations. There's no 1/n correction, so why were there 1/n correction before? Or said differently, since any linear combination of the primaries would have been okay, why a particular combination is chosen to be the bulk field? Okay. And what I want to argue now is that actually from the point of view of the CFT, the problems that originating from the chi equal to 1 singularity, and particularly the branch cut between 0 and 1, actually are a problem from the point of view of CFT. And that in fact, the 0th order smearing is not a good CFT operator. And I will need to explain that. Okay. So, as I said before, when you insert this inside a 3-point function, you get an expression that has this chi equal to 1 singularity. And it's true that the chi equal to 1 singularity gives you, it's not the correct analytic structure since they're all space-like, but that's not its only problem. It turns out it has a much bigger problem with it. And the problem is that, in fact, in the presence of this chi equal to 1 singularity, the I epsilon prescription of avoiding singularities in Lorentzian correlators and of fixing what is the order of the operators in the correlation function is ambiguous. So I think it's best to get a concrete example just to show you how things work. So let's say you have ADS3. We have 3 operators, all of dimension 1. So O2 and O3 are dimension 1. They're at some position that I labeled here. So the position of O2 is at t equal to 0 and minus y. The position of O3 is at plus y. And phi 0 is the smearing of a dimension 1 operator. And then you get this function, which is a little bit simpler than the hypergeometric function, which was a general result. And in this particular case, you get a simple log result. And there are various expressions here. And you, as I said before, in order to get this result, you compute in a region where there are no singularities, and then you only continue into a region where you want. In particular, the equal to 1 region is a region that you cannot go into without crossing any kind of singularity. So you have to cross some singularity. Okay? And the question is, as you cross into that region, what does your I epsilon prescription tell you? So here is, I drew this diagram here. So this is the boundary coordinate x and the bulk coordinate z. And the region 2 here, between the 2 blue lines, is the region chi between 0 and 1, and the blue lines are chi equal to 1. And I can start with a bulk operator, let's say, around here. So this would be smeared here, and I could then analytically continue into region 2. I could start with a bulk operator here and continue to region 2. The red lines are chi equal to 0 singularity. Or I could start with a bulk operator here, and I could analytically continue like this into region 2. And I can cross at any point. Once I cross into region 2, I can, of course, go without singularity. And the I epsilon, there's a branch cut from the log. And which branch cut you are going to be depends, of course, what is the I epsilon when you cross singularity. And in usual field theory, of course, this doesn't depend on how you cross the singularity or where you cross the singularity or how you got to the endpoint. It's always the same. And that's the condition that things are well defined. However, when you look at what happens here, it is not quite the case. What happens here is that analytic continuum from a variety of regions may end up giving you a different I epsilon. For instance, if I cross from region 1 to 2, I can get a total plus I epsilon. But if I cross from region 3 to region 2, I can get a minus I epsilon. So in that sense, the correlation functions are ill-defined. Now, this does not always happen. I will explain when it does. Yes?
Interpret the previous expression as a sum over modes in the CFT. So about the vacuum of the CFT, you have an infinite tower of modes that are discretely spaced. And that should give a natural regulator for the correlator, which is free of all
No, I will give a slightly different version of this for no. The sum converges, but it actually, as you vary the parameters, near chi equals 1, the sum diverges. It will not be a regularity. You actually have a singularity, and your I epsilon prescription gives you how you go around the singularity. The chi equals 1 singularity is unavoidable.
That's fine, but so what I would imagine is that you take a sum over modes, you cut it off at a larger but finite number of modes, and when you're exactly at that point, you'll get some large number, which you ignore because that's the point where things are singular. But as long as you're away from the singular point, that should give you a well-defined answer. The prescription is you really take a finite sum of ADS modes and so that kind of thing gives you a large number when you're at the singular point, a finite but large number, which depends on the cutoff, and when you're away from the point, it doesn't give you anything bad.
That is true, but I don't think this is the right prescription. I mean, once you cut the sum of modes, you never have any kind of locality in the bone. This is...
yes, but you have locality up to 1 over the cutoff. If you cut off the sum of modes a large number, you get locality up to that scale, and that's...
It's true, but we're, I think, trying to mimic what we actually get at when you just do perturbation theory in 1 over n.
So I'm not denying, of course, that you will need, of course, you need to add these terms to get the right expression. But I'm just objecting to the idea that the zeroth order guy is not a good CFT operator. That's what I'm worried about. That's a much stronger statement. That in the statement.
I understand, but okay. I mean, this is some evidence. How you interpret it, you may decide differently, but I'm trying to explain that the expression that we have, and it's not so, I'll explain a little bit better why it is so and what you might expect this to be. It's just not a well-defined expression, and I'm just giving here the evidence. This is certainly true. You might want to interpret it differently. Yeah.
So this tells you that the correlators that you're calculating with this big phi operator is not a time-ordered.
No, it's a Whiteman correlator.
But you're calculating a Whiteman operator.
Yeah.
And you're asking for. So sorry, there's something that I did not understand. So the statement is that it doesn't obey the correct imaginary parts you would expect from a Whiteman operator. Is that the statement?
Here it says that the Whiteman correlator is actually ill-defined because the way you continue to get the Whiteman operator from regions where there are no singularity is ambiguous.
Okay.
So the Whiteman correlator of phi 0 is ill-defined in the way that we know how to compute it.
So so this correlator is really defined in some many branched space. Is that another way of saying it?
Well, how to interpret this issue will be the next, and we'll give what we think is the correct interpretation, but it certainly is not a provable. I mean, certainly there might be a different interpretation, but we will give what we think is the correct interpretation. So, the 3-point function is not well defined. But in fact, it is not always the case. It happens only if it depends on the way you order the fields. So, the I epsilons that you give depends on what order you want to have the fields in. So, in this order, the epsilon for this guy is bigger than the epsilon for this guy, which is bigger than the epsilon for this guy. And if you want to do any other order, you have to choose a different order. It turns out that actually, in this order, there is no problem. And also, if phi 0 was totally to the right, there is no problem. So one could say that, but when phi 0 is in the middle, that's where there is a problem. So this sort of says, in some sense, that phi 0 acting on the vacuum is a well-defined state. But that state cannot be promoted to an operator in the same way that we think that state-operator relationship hold. When you move it inside between O2 and O3, it's not a well-defined thing.
Saying a notation correctly, is this negative ADS mass, like negative mass in ADS?
Negative?
Is Is this in the Brighton-Lohner-Friedman window?
No, this is massless.
It's massless.
So I guess this would be 2. Yeah, 2. Sorry. This is massless field in any case. This is just an example you could work out for the general case, and it's the same. And so, as I said, it only happens when phi 0 is in the middle of the 2-point function. So I would want to say that phi 0 is ill-defined as a CFT operator. And you might wonder, how did this happen? After all, well, we started it as either writing as a smearing of a conventional, of an operator, or actually phi 0, you can expand this and write as an infinite sum of a local operator. And what happens is that when you compute the 3-point function, each term in the sum is well defined, but the sum diverges and you have to only continue. But the way you only continue depends on your I epsilon, which are already fixed by the order of the operators. And so that I epsilon, that continuation becomes ill-defined. Thought about differently, the smearing function, it's actually not unexpected. So usually when we think about field theory, we have some local operator, O in this case, in the CFT, and we can smear it to get, so they are considered as tempered distribution. You have to smear them, and with some very nice smearings, which are continuous, differentiable, infinite differentiable, etc., and then you get well-defined correlation functions. But in this case, the smear that we use is, at most, it is continuous, but not differentiable in any way. It has a delta function singularity in its differentiation, and so this is a very bad smearing from the point of view of somebody who does field theory, let's say in the CFT. So you might expect some problems to arise. You might expect that this is not a well-defined operator because of the singularity that can happen. Yeah.
So this, this phi 0 you are defining using the modular Hamiltonian.
You can define, well, yes, you solve it.
Okay.
You can do that.
So when you put phi 0 in between this O2, O3, do you use the modular Hamiltonian of the interval in the vacuum, or do you use the modular Hamiltonian after you act by this O2 on the vacuum?
Use the vacuum, the modular Hamiltonian in the vacuum. Well, I mean, you compute the 3-point function, you don't use the modular Hamiltonian, but it's true. Phi 0 that you use is the phi 0 in the vacuum.
But when you're calculating with the phi 0 in between, if you use the modular Hamiltonian after you act by O2, will that solve this problem?
Yeah, so, well, we thought about this issue. I don't think this is where things come from, but it's a bit longer discussion than I could, but yeah. Okay, so phi 0 is not well defined in the CFT operator, and so, but the problem really comes from the chi-equal-to-1 singularity. You see, usually when we have singularities, the singularities that depend on the position of 2 operators, okay, and then you have epsilon 1 minus epsilon 2, and you're in there on this or that branch. But chi-equal-to-1 singularity is something that depends on the position of 3 operators. Okay, if you remember the picture, it was when the bulk operator hits the RT surface, which was defined by both y1 and y2. Changing either one of y1, y2 would have changed where the singularity occurs. And so you might realize that when you look at the total epsilon of the singularity, it will be mixed between epsilon 1, epsilon 2, and epsilon 3 in ways that may become problematic, and this is actually what happens. So it's really the fault of the chi-equal-to-1 singularity. And so the only way to avoid this problem is to not have a chi-equal-to-1 singularity. And in fact, the prescription that I gave before is a prescription that changes phi to be an operator, phi 0 to be an operator by addition of the double trace operator to something that does not have the chi-equal-to-1 singularity. But this argument is completely in terms of the CFT framework. Oops. In this point of view, the chi-equal-to-1 singularity is not a problem because of bulk causality, but is a problem because of the CFT operator becomes ill-defined. And the point here, so why is this nice? Well, first, it's a completely CFT reasoning. And second, as was asked before, it is better suited for the situation when you have interaction with gravity and gauge field. So when you have interaction with gravity and gauge field, you have the Gauss law constraint. You still want to avoid this chi-equal-to-1 singularity. You don't ask for the correlation function to be analytic at space-like separation. You just ask them to be well-defined. And the end result of the procedure will give you something that is not local in the bulk, but only has singularities that do not have this problem. So the chi-equal-to-1 singularity is gone and is left with a singularity, which is the conventional one that comes from the Gauss law. Yeah.
Even at zeroth order, there's some ambiguity in the smearing function in position space, because you can add these, space-like modes which don't propagate in ADS to change the support of the smearing function. So is the problem that you mentioned specific to a particular choice of smearing function where you choose things to be exactly local? If I choose some smoother smearing function, then this problem may not occur. In fact, that's what I was referring to when I said you take a sum of modes. That may not have precisely the position space expression you mentioned, but it's also a good smearing function at order 0.
Well, I actually think this is the best smearing function to do computation with. The other ones with the extra space-like modes are not supposed to change any of the computation. They're supposed to be give the exactly same result. So computed at regions where there's no singularity, you would get the same hypergeometric function, and the continuation would be the same. This ambiguity in the modes does not appear here because actually the Modular Hamiltonian fixes that ambiguity in some sense. You could have asked that Modular Hamiltonian commutes with phi up to some things that are 0 in the vacuum. So that would be some, but if you exactly ask it to be as an operator commuting with phi, then those ambiguities are lifted. It's not that it's better than other things, it's just part of the procedure. Okay. Yeah.
That in the bulk, if this phi, another operator phi approaches this geodesic, then it gives this singularity. So it's like when two operators are approaching each other, it gives this singularity. So that is like a physical singularity in quantum field theory, right? Means normally that's how we see physical.
Well, in terms of this picture,
yeah, this
in terms of this picture, so the way that it works, so when you look at the 3-point function, phi 0 now, if you look at this 3-point function, the only contribution would be from a 2-point function of phi 0 with itself, which is one of these operators, integrate over the geodesic. That would give you a singularity. Now, however, if phi 0 is, you add some stuff to it, then there will also be the singularity of those stuff approaching the RT surface with some other operator, phi 0, corresponding to them. And the sum of those singularities, the ANs that I was talking for, was to make the sum without a singularity. So if you think about it, you have some branch cut, you have some monodromy, and the sum over the monodromies would be 0. That would be the condition for the cancellation of the chi-equal-to-1 singularity. Okay.
So in that sense, it's not like a physical divergence. This chi-equals-to-1 is divergence is not a physical divergence. Is that?
It is not a physically expected singularity if you think about bulk theory. But the point of this is that it's not actually a physical singularity, even thought of from the point of view of writing down CFT correlators. Okay. Okay. So that what I thought now was that we have now a new interpretation. We both can compute phi 0 as just coming from the Modular Hamiltonian. I don't need to know what the bulk metric is. And once I have that, the only thing that I require is that phi 0 would solve the Modular Hamiltonian equation and, as an extra bonus, be actually a good CFT operator. That actually fixes the operator phi that it turns out has all the nice properties that we want from bulk operator. However, it raises a slightly a disturbing issue. So what we're trying to do here, after all, is that the operators that we're writing as CFT operators will be the operators that we build the bulk Hilbert space. They will act on the, let's say, the vacuum, and then they would build up excitations, and that's how we will build the bulk Hilbert space, and how we embed the bulk Hilbert space into the CFT Hilbert space. And if before we thought that, okay, this is you could do in perturbation theory 1 over n, you can add more and more stuff, cancel the chi-equals 1 singularity in perturbation theory. We don't, of course, expect this to be true beyond perturbation theory. And before, you could view that the breakdown of perturbation theory would result in some operator that you could not correct. But, okay, you don't expect from bulk physics to be local, non-perturbatively, and that's just the breakdown of locality non-perturbatively. Now, things are much worse, because what I said was that actually we should not view this as a good CFT operator. So if we cannot correct this chi-equals 1 singularity, the resulting operator is not a good CFT operator. So, in principle, I could only build the bulk Hilbert space in a perturbative way, and beyond perturbation theory, I cannot actually build the bulk Hilbert space. It is only an approximation that I have a bulk Hilbert space and bulk excitations. This is somewhat disturbing. And the question is, what can you say about this? And so this is sheer speculation about the thing. So you might ask, well, you start with seemingly well-defined operator. Let's say you write phi 0 as an infinite sum, and each one of each term in the sum is a well-defined CFT operator. And it's true that when you have infinite sums, things can go bad. But usually some of the properties of the original operators just don't go to the infinite sum. And the question is, which property in this case? And the only culprit in this case, we believe, is the associativity. So we'd like to claim that phi 0, well, what happens is that the singularities associated with the infinite sum turn it into a non-associative operator. And why would we say that? Well, so being a non-associative operator, it means that when I put it, let's say here, I could think about first multiplying it with O2, and only then multiplying with O3. Or I could first multiply with O3, and only then multiply with O2. These are certainly two options. And we would want to interpret that the different I epsilon prescriptions, which we have a branch cut, and it could either have plus epsilon or minus epsilon, would correspond to actually two different ways of multiplying. Now, what is the evidence for this? Well, one evidence for this is the following. We have phi 0 as an infinite sum, and each term in the sum is associative. So how would we know how we multiply each one? One way to sort of enforce it would be, would take the O3 and put it very, very far away. In that sense, it would be natural to think that in this limit, phi 0 first does an OP in with O2, it's some OP expansion, and then we do the correlation function O3. Or we could do the other limit, where we take O2 to be far away, and first this multiplies. And indeed, when you check these, and both of these are in the chi-equal to 1 region, and when you check, you see that indeed in this case, you get a different I epsilon. So if this, let's say, was plus I epsilon, this case would get minus I epsilon. So the I epsilon prescription and the way that you could do the P in sort of a very intuitive way agree. So we might think about phi 0 in some way. This is not very helpful, but maybe it's a clue to what is the correct structure that we might expect if we wanted to build things. There's a nice property with that, okay, this is not so important with respect to the time. And so, as I said before, bulk perturbation theory breaks down. There seems to be a problem with the Hilbert space. So this was discussed in different contexts by Gautam and Raju. So we seem to come to a sort of semi-conclusion that bulk quantum mechanics is at best something that arises from the CFT quantum mechanics in a perturbative approach, and that there's some other structure that underlies, if there is any, that there should be some other structure. It's not the regular quantum mechanics for quantum gravity. There's some other structure that underlies it, that in perturbation theory becomes an associative algebra. But in fact, originally it is not. And that's everything. Thank you.
The other questions.
Can you say again why beyond perturbation theory, the theory must become non-associative? We know very little about this, so where does the claim come from?
That is true. This is more, I would say, a belief than a proof. One way to think about it is that you may ask, so when you add all these corrections, where are they? You add all these corrections, and you may ask how many primary fields you need to get to have this. And it looks that these primary fields, you can connect them to some kind of modes in the ADS, and so having the local bulk fields would give you basically build a Fock space in the bulk using these operators. And so if you could do all this in order n, you will get a full Fock space of the bulk theory, which whose entropy scales wrongly at high temperature as compared to the CFT maximum entropy, which is n squared t cubed. So that's the usual argument that people would give, that you cannot really have so many. Now it's true that this argument is somewhat, it's not very precise, but that is just a belief.
Is it understood how these statements change when you consider non-vacuum states, say thermal states?
I would think they don't change.
So you think there'll be similar statements in the thermal state in constructing operators?
Certainly the Modular Hamiltonian that we did, and we got the correct smearing function. Interaction we did not do. It's more complicated. You see, in order to do the interaction, you at least need to know what the three-point function is. You know that in vacuum, in other states, you just need more information. But it would be very strange if it worked differently. I mean, the only thing is to find tools that are generalizable to other situations. So I would believe it works the same way, but of course, you never know.
Hi, so, hello. How is this n related to G Newton?
Well, I mean, the n squared is the central charge of the CFT.
So is it okay to take higher order perturbations in n while keeping gravity off?
I'm not keeping gravity off here. I just didn't tell you. So when I look at the three-point function here, the example that I gave was when these are scalars. But you can take the example when, for instance, one of them is the energy momentum tensor. So that would be a coupling of bulk field to gravity. And you can compute the three-point function, and it turns out that it has a similar problem. And again, you have to add stuff. There's a complication, because the stuff that you need to add, which is this, here in the scalar case, you actually can make primary scalars from the OJ and OK. But if you have an energy momentum tensor that is conserved, you cannot make from the other scalar and the energy momentum tensor primary scalar. You can just make something else. And that makes this formula a little bit more complicated, but we could still do it, and you can still get the cancellation of the chi-equal-to-1 singularity in this case.
Sorry, this may be a very loose comment, but I was just wondering, because of this non-locality, and now that you think that there might be also non-associativity associated. Sorry, non-associativity. I'm just wondering because I think it's known that if I have closed string theory with some background H flux and so on, then the geometry itself can become non-associative at some level. And this description, I would presume also has some non-locality inbuilt. So do you think that this description is somehow hinting that there might be a non-commutative description of the system, or?
Non-commutative or non-associative?
Well, if I have some H flux but with a closed strings, then the geometry itself will become also non-associative. So I'm just wondering,
Yeah, I'm aware of those works, and when we were trying to think what this non-associativity might, how to handle it. After all, this is not the first time non-associativity. If you take a particle in the background of magnetic monopole, you also get non-associative algebras, and people have thought how to deal with that, but as far as I could see, there isn't a very clear framework to do that. So, this problem of non-associativity has come up before, but I'm not sure, at least to my understanding, what is the actual framework that replaces things in a well-defined way. There's some ideas, but yeah. Here, it's not the geometry that becomes it's a little bit different situation, and I'm not sure I can use those machineries to understand this in that way.
Yeah, general question. So you have this 2f1 function which has three singular points, 0, 1, and infinity. You stress a lot the chi-equal-1 singularity. One of the other singularity must be like the boring Euclidean limit, the OP limit. What's the other one?
The chi-equal-to-0 singularity. There's singularity at chi-equal-to-0, which is the usual light cone singularity. So the singularity at chi-equal-to-0 only depends, the epsilon of it would only depend on either epsilon 1, epsilon 2, or epsilon 2 and epsilon 3. It doesn't have this problem.
Yeah. Okay. Yeah, I see. So the Euclidean case, you start with chi equal infinity. Then there are two different ways to cross to chi smaller than 1.
Yeah. So
what about are there real kinematics which take you around the branch cut at 1 and go back to chi equal infinity? Because more should be true. The analytic, it might be true that in some limits your correlation function is to remain bounded or something like that. That might be more constraining than what you already put in.
That may be. So I've always viewed this more of a Lorentzian thing. So from this point of view,
yeah, this is exactly why. But
maybe you have to go on the complex plane.
No, I don't want to go complex, but I want to explore more extreme Lorentzian kinematics.
Which would be what? So here is the chi equal to between 0 and 1. You take this, for instance, region, and you expand the sort of perpendicular light rays between them. So think about this is in ADS3. It's very simple to picture. Think about this as the RT surface. Then this becomes the bifurcation sphere for a Rindler wedge in the bulk, and the chi between 0 and 1 is the forward region of the black.
So the region will be that might seem interesting to me will be something like the rigid limit, why y2 goes to the infinite past and y1 to the infinite future.
Ah, that limit, I see. We haven't looked at that. So these are time-like, you mean? We looked at what happens.
No, they could stay space-like. I don't think that's the big deal, but it's one is in the past of phi, small phi, and the other is the future. That would be the important part.
Yeah, well, we haven't looked at that. Maybe we can talk and explain to me what you...
So I have one more question, if there are no other questions. So there's this proposed proto-field that Kaplan and Fitzpatrick and others, which basically is in ADS3 a field coupled to pure gravity. So would this complaint also apply to those operators, that those proto-field operators are not good CFT operators? Is that the claim?
Yeah, I cannot answer that. I've looked at that paper and trying to understand what it says.
It should, right? Because there's no phi I, phi j, phi k coupling there. So, if you really want to construct a bulk local field with bulk interactions other than just with gravity, you will need to add a sum of protofields. So it's like an enhanced version of phi 0. With gravitational effects.
What they do is enhanced version of phi 0. You might say, I mean, if you think about the modular Hamiltonian, they have some other operator which constrains. So the modular Hamiltonian gives you really the building blocks that you have to build things from. And what they have is building blocks where it's already dressed with all the, with some of the gravity interaction. But I would suspect even in there, I'm not sure if the full prototype field is well defined, but again, it's a little bit hard to decipher it now.
Okay, so if there are no other questions, we thank the speaker again. So we'll break for coffee now, and let's try and be back by 11:05.